What is going on with vertical springs? I want to take some time to just really explain why a mass on a vertical spring oscillates about the new equilibrium position as if that were the unstretched length of the spring at exactly the same frequency as it did before and as if gravity didn't exist. So let's take a quick look. Hopefully I can do this in 5 minutes or less. I know that's ambitious, but let's see. So here's a spring just hanging, no mass, it's at its unstretched length. Now I'm going to come along and hang a mass from it so that it has an equilibrium length, which I will call x sub 0. Here's a mass m, it has a spring constant k. That's its new equilibrium position. The spring has actually stretched a distance x naught. So this distance, I'm going to do it the right way. This distance here is x naught. Now that equilibrium position of the spring tells us that mg equals kx naught, and that will be useful to us later on in our derivation. Third thing we're going to do is now we're going to deviate the spring below x naught by some distance I'm going to call x. And if this is undergoing simple harmonic motion, it means that, and I'm going to make this red so it super stands out, it means that the spring is going to oscillate around this equilibrium position at an amplitude of x, and x will vary with time, as if gravity doesn't exist, at the same frequency that it would oscillate at if this were just like a sideways mass on a spring with spring constant k pulled some distance x sideways. So just to really draw a picture so you understand what the equivalency is here, this is really going to be the same as if I had a sideways spring of spring constant k, that's x equals 0, and I deviate it a distance x away, so this distance, this is going to just oscillate around that equilibrium position the same way this spring would oscillate around its unstretched length. There's no difference. That is totally weird. That is super non-intuitive, and we're going to see why it's true. So if that's the case, what it means is that if the equation for a harmonic oscillator must apply in x. So negative kx, the restoring force, must be equal to the second mass times the second derivative of x with respect to time. That's often written as negative k over m times x equals d squared x dt squared, and we know negative k over m is equal to omega squared, and so if the k over m is still there like k over m, it also means it's oscillating at its original oscillation frequency that it would if it were just a regular mass on a spring. Okay, so let's see if we get that result. Let's come back to our picture with the mass fully deviated from equilibrium. And let's look at the forces acting on the mass at that point. We know that gravity is acting down, and I'm going to go ahead and define down as the positive direction. The other thing I'm going to do is I'm going to call this x equals 0, and I'm going to define a variable x prime, which equals x naught plus x. That's the total amount of stretch truly inherent in the spring from its natural unstretched length. If that's the case, there's a force acting upwards equal to negative kx prime. Since the spring is stretched x prime, it's trying to restore with a force equal to negative kx prime. Coming over here and writing sigma f equals ma, I get mg minus kx prime equals m times d squared x prime dt squared, because that's my true position of the mass. It's x prime off of x equals 0. The first thing I'm going to notice is that if x prime equals x plus x naught, then d squared x prime dt squared equals just d squared x dt squared, because x naught is a constant. So if I take the derivative of x naught, it's just going to go out. So really, since x is the only thing that's varying, x prime will just be dependent on the evolution of x. So that's cool. I can substitute mg minus kx prime equals m d squared x dt squared. And you could see I'm one step closer to where I want to be. But the left side of this equation still isn't adding up. So I'm going to come along, I'm going to take my x prime, do that same substitution, x prime equals x plus x0, mg minus k times x plus x0 equals md squared x dt squared. That's mg minus kx naught equals m d squared x dt squared. And that still doesn't look very good until I remember that mg is equal to kx naught. Then if I can substitute, I get kx naught minus kx naught equals that. The kx naughts don't matter anymore, and I get negative kx equals m d squared x dt squared, which, if you remember, is the equation for a simple harmonic oscillator oscillating around a displaced equilibrium point. So when you see a mass on a spring and it's hanging vertically, you don't have to do anything. You don't have to think about gravity. All you have to pretend is that whatever amount I displace it, it's going to oscillate around that new equilibrium position, just as if that were the natural length of the spring. The only time you have to go back to reality is when you're thinking about, someone asks you, for example, how much energy is stored at this moment? Well, then you have to go back to the fact that the spring is stretched a distance x prime, and you need to calculate the energy that way. But even in terms of, like we did in class, looking at what's the velocity at this equilibrium position, you could pretend that the energy here is just 1/2 kx squared, where x is just your distance off of equilibrium, and that becomes 1/2 mv squared, the velocity over there. You can essentially ignore the effects of gravity